Okay, as I mentioned, for the first few days, we are going to lecture in lab 2. So lab is not lab, it's just lecture. We're going to go through what we are supposed to do to kind of catch up with the schedule that we have. Okay? As usual, I'm going to create a new project. And the project is going to be in the repository as usual. So we're going to go to OOP345. And we're going to go to NRA, which is our section. I'm going to select the folder, so it's going to be 02, September 09th. Create it. Okay. Properties, close it. I need only Solution Explorer, so I'll stick that one around. Change the properties to C++ 20 standards, and as usual, we're going to add prg.cpp over here, and then add. Testing if everything's okay, so include IO stream. At the end of the class, you can see it or make it bigger. Bigger? Are we good? Bigger? Is it good now? All right. STD. So OOP345, NRA 02, September 11th. Okay, just want to make sure everything's good. Compile and run, make sure my compiler is set up properly, and then we are going to start. And everything's good. Okay. So let that be. And at the same time, I'm waiting for my browser to run. Okay. Make everything ready in here. All right, so we're going to look at the fundamental types a bit more closely. We mentioned that every variable in C++ has a type that tells the computer how to interpret the bits stored in memory, depending on what the type is, and what operations are allowed to work on that data. The most basic building blocks, as we mentioned, they are fundamental types. You cannot break it down into smaller pieces. And they include integers, floating point numbers, booleans, characters, and some related concepts to that. Okay? So integers are essentially whole numbers, no decimals. So 0, 1, or I'm going to put a-hello.cpp. And then we continue after that. So integers. There's one thing over here missing with integers that I mentioned that I'm not putting it over here. It's like, as a convention, it's not part of this, but they are integers. I didn't put character over here. Character is actually an integer. We don't have characters in C++. So I should have put over here what character. I'm not doing it just, but you know that characters are literally integers, minus 128 to positive 127, or if it goes unsigned, it's from 0 to 255. And short integers, 2 bytes usually, integers, 4 bytes usually, long 4 bytes usually, and long 8 bytes. And if you look at line 8, there's a capital L at the end. That actually indicates that the literal value at right is actually kept in a long format. And the other one shows that when you put LL over there, that means that literal value is long. Okay? If you do not mention, by default, obviously it's going to be, and by default it's going to be an integer. And when you are setting a short to an integer, it automatically downcasts it, and we know that as coercive polymorphism. And the outcomes are obvious. There is no hidden agenda over here. Just run it, make sure everything's good. And we should realize that for every single integer that you have an unsigned version. So these are integers. We have an unsigned version for whatever that you have over there, okay? And essentially, if you add unsigned in front of an integer, you are literally removing that signature bit from the bit pattern of the integer, and therefore the size doubles and no negative values are there. So if I say unsigned integer u, then I can actually write the literal value. So if you have L, it will be UL. If you have LL, it's going to be ULL. That essentially means, so you add a U, and literally that makes it an unsigned integer. They don't accept literal values, and you know that every single primitive value loops back on itself. So essentially what I mean is that when you have a value, so this is the value that I have, okay? It goes to positive, and it keeps going up, and it comes back to itself. So this is 0, and this is an unsigned value, and this is the maximum value that it can take. If it reaches to that maximum value, it goes back to 0. It's always like that. It's the same thing with negatives and positives. So when you're talking about negatives and positives, again, you have your value, and the value loops back on itself, which means over here it's going to be 0, and at this place, so let's put it, this place is 0, and then it goes up positive to a value that you have. If you go more than that, it's going to jump back to the negative side, and the other one, something like that. If you go less than certain negative value, it jumps back to the positive side. These are called overflowing. So if you have minus 127, minus 128 in a regular character, and you reduce it by 1, it becomes positive 127. And if you have 127, you add 1 to it, it becomes minus 1, and so on and so forth. So just keep that in mind. This is something that you need to remember. Sometimes when you are writing code and by mistake you pass the borderline of the capacity of your fundamental value, suddenly jumps back to the exact opposite thing, and this usually causes endless loops and things like that. So be careful about it, especially when you are going up to a limit that is beyond the fundamental type. So if you have a character as a for loop and you test the value to see if it's less than 500, it's going to be an endless loop, because no matter what, as much as it gets higher, it always remains lower than that value, and it keeps going like that. Keep that in mind. Floating point types. We have, for floating point types, so this one, These are easy stuff. That's why I'm going through it quickly, so we can just see. Floating point types are they are not calculated the way they are calculated for integers. So for integers, whatever the number of bits you have, 2 to the power of that number, it becomes the maximum thing that it can accept. And if you have a negative value, it's 2 to the power of max number of bits minus 1. So if you have a 32-bit integer, the maximum, if it's a signed integer, maximum number that it can take is 2 to the power 31. So that's how it works. For floating points is not like that. They're calculated by precision. Okay, so which means 7 digits. If you have 7 digits, that's the precision of the number. If you go more than that, you lose precision. So right now, if you look at it, 3, 1, 4, 1, 5, 9. If you count 3, 1, 4, 1, 5, 9. If you look at the number that you have over there, it's below 7. Therefore, you're good. If the number goes more than 7, then you lose precision. It means you lose value. Same thing for double. Double, so for I'm sorry, for floating points, it's around 7. For double, it's 15 digits. And for long double, it's much more. It's 100 something, I think, 128 or something. I don't remember what it was, but it's very, very precise. But yeah, so that's essentially what it is. Let me just make sure it runs. Yeah, everything's good. When I say floats, essentially it means real numbers, but when I talk about precision, what do we'll come to it so we understand exactly what does it mean, precision. When we are talking about precision, let's put it this way. If I put this number, so when I say 7, what do I mean? I don't know if anybody ever told you that, but so if I go like this, 1, 2, 3, 4, 5, 6, 7. This is okay. Okay, significant digits. That's the number. Zeros over there don't matter. If I add an 8, I lose precision. Why? Because where the dot, when the floating point is only at, it will only add to the number of exponent over there, 10 to the power of whatever. Therefore, those are not important. How many digits back to back you have over there, that's the precision that you have. So essentially, if I have this, or these are good. These are okay. These are precise. But as soon as I go like this, then I lose value. I lose precision. If I go like this, I lose precision. Got it? And it's the exact same thing for the double value. So 7, okay. So this one is okay. Precision. Okay, so you got to be careful about this. It's the same thing over here. That's why floats are rarely used, because as soon as you do some calculation that the number of significant digits go more than 7, then all the calculations go imprecise, even for double. So these values are not used for accounting stuff, because after lots of calculations, you're going to start using pennies. Okay, got to be careful. This is okay. This is not okay. So that's that. Zeros don't count. And I'm gonna add this over here, so essentially you can okay? Oh, sorry, Alt FA. Shortcuts are Unicode character. Yeah, it's fine. Okay. So that's about fundamental types and floating point precision. Now we're going to go to something a little bit more problematic for new C programmers, pointers. Okay, so we're going to talk about pointers. If you think there's any problem, you have any problem with pointers, we can have an extra session for it. I don't know, an online session or something. I can actually go through what I do with IPC 144 with my pointer lecture. I can actually do them and tell you what the pointers are. But my advice is that don't think of pointers as anything special. Pointers are simply variables. So any pointer that you have when you're saying integer pointer, when you're saying, don't give them extra credit. They're just unsigned integers. That's all. So a pointer is essentially an unsigned integer. The only difference, let me just put the code for you over here so we can see. So when we are talking about pointers, I have x over here that has value of 42 that I'm writing over here int, and I put an asterisk over there. When I put an asterisk over there, that essentially means that p is an integer pointer. Asterisk doesn't belong to p. It belongs to int. Together, they mean pointer. You want me to quickly take you through the lecture of pointers from C? Would you like me to do that? Let me see if I have it somewhere in here. PowerPoint. What is the extension of PowerPoint presentations? Anybody remembers? PPTX, I think it was. Anyways, let me just go like this. Just a second. Let me pause the recording over here. Resume, recording over there. Is there any question over there happening? I hear someone talking. You have a question?
Just helping him.
Oh, okay, okay. Okay, so got it? Okay. All right, so when you're dealing with memory, this is usually what you have. You have the memory of your computer is essentially a big array of bytes, okay? And the address starts from 0, goes up to the amount of money you have in your pocket, how much money you pay to buy RAM on your computer, right? So it keeps going as long as you. So essentially the address we talk about, it's the index of the byte, which what do we call a byte in What do we, actually I forgot to put this in, what do we call a byte in C language? A byte in C language is a, you remember? The type of a byte. What is a byte in C language? Seriously? Pardon me? Yeah, but what is the type? In C, if you want to create a byte, what type of variable you create? You create a, what is 8 bits in C language? Seriously? Character. Char type. Char is a byte. Char, I just mentioned char is an integer. It's 8 bits. So when I say byte, in C it's char. Okay? Got it? All right. So how many characters is an integer? 4. Of course, those are not characters. Back to back, together, it's a fundamental type. Okay? So anyways, these are the number of bytes that you have in memory. So what happens is that whenever you create a variable, integer var, a piece of memory is set aside and it's labeled with the name of the variable, and then that's what you're using. So when you say int var, it picks a piece of memory and that becomes your variable, right? And when you say double var, because the fundamental type is 8 bytes, it allocates 8 bytes for you. Are we okay down to this point? Right? Okay. So obviously, when you set that variable to something, it sets the bit pattern of what the number is to the entire 4 characters, 4 bytes, right? We good down to this point? And the exact same thing happens when you set the double one. So if you have a double value, whatever the bit pattern of that one is, sets the 8 bytes to that one. Are we okay with this? So how does it know? It needs to set, when you put this thing, it needs to translate this to 8 bytes. It's from the type. So when you put this value and you say put this value in a double, it knows this has to be either converted to a double. If it's a double, it should be used, and it should be going through the whole. It's impossible for you to set a double to a value and only set first byte to get set to something. It's one unit. It's not like a string that you have 50 characters in it, and each character is an individual element of an array. When you are saying double is 8 bytes, it means if you put 0, everything will become 0. When you put a value, everything. Are we okay with this? Do we understand this? Okay. So that's how variables are set up. So now that we have the variables, let's together design something to be able to hold the address in which they are sitting in. Now, what is the address of the double in here? Who has the microphone? You have the microphone? Oh. A ghost has a microphone. Okay, put it over here. What is the address of the double over there? Where does it start in the memory? 132. Obviously, it's not 132. It's the number that you have is essentially 23,423,132. Okay, that's the thing. So you see, I only put the first 3 digits, so it's easy for us to comprehend. The numbers are much bigger than that. That's the number that you have. You can pass the microphone to the gentleman over there. Okay, so now, we want to design something to hold that value. Now, from what you saw, it is impossible for those values to be negative, correct? It has to be a positive value. So let's create a type and call that type a pointer. So literally create something called pointer. And I say pointer PTR. So when I say pointer PTR, we know that depending on if you have a 32-bit machine or you have a 64-bit machine, the addresses can get bigger or smaller. We'll assume this is a 32-bit system, therefore 4 digits is enough for us to hold as big as number that we want for our address. So when I'm using that PTR over there, that is a variable that is supposed to hold the address of other variables, not their values. Essentially, if I want to put the address of var, what's going to go in PTR? If I want to put the address of var in PTR, what's going to go in PTR? If I want to put the address of var What should I set PTR to?
You set PTR to
108.
Yeah.
10. If you can't,
I can see.
because I see you're trying to kind of figure out what it is. Okay, so for all those people who have weak eyes like me, please come to the front seat. I'm not going to beat anybody in close by, trust me. But for some reason. So PTR should be set to 108. And pass the microphone, please. Immediately when you answer, get the habit to pass the microphone to the
You can
next
still
one.
remain here though.
That's okay. All right. So if I want to set the PTR to the address of the double, what's going to be the value?
132.
132. Fantastic. So we know what we are doing. So I can put any value inside that PTR. I can put over there something like, let's say, 102. But if I put 102 over there, I'm essentially saying something that's sitting in address 102. But there is nothing in address 102, right? It's like you put a wrong address on an envelope. It doesn't make sense, okay? So I need to actually point to something, like 108 over there, so it actually points to that value. The problem is that when you are actually writing code, all you have is the name of the variable. You don't have what the address of the variable is. So what happens is that we're going to come up with some kind of an operator that extracts the address of a variable instead of its value. So I need to be able to say PTR is equal to address of var. You see this? So let's say address of is something that extracts the address out. So when I say when PTR is equal to address of var, it actually sets that one. Now that I have the address, I can indirectly play with that PTR. So if I say, for example, the target of PTR is 2345, what am I saying? I'm saying target of PTR. So I'm not talking about PTR. I'm talking about what is the target of PTR. If I do that, if I say 2345, then what's going to be set to 2345? What do you think is going to be set to 2345? When I say target of PTR is 2345, what PTR is pointing to? It's pointing to?
2, 3.
No. See, PTR is address of var. That's why it has 108 in it, right? Now, when I say target of PTR is 2345, it means I have to go to PTR, see what PTR is pointing to, and set that one instead. Now, PTR is pointing to where? 108. Perfect. What is sitting at 108? var, right? So when I say target of PTR is 2345, this is what I'm going to see. The target becomes 2345. Are we okay with this? Any problem with this? All right. So essentially, if I print the variable that I have, what's going to get printed is 2345. Look at the bottom of the page. If I print target of PTR, still 2345 is going to get printed. But if I print the PTR itself, then the address is going to get printed. What I have in PTR, which is 23432.108. Please look at these printouts and try to digest what is printed over here. See if you have any problem with it. Yes?
So when you say target of PTR is 2345, does it mean that the value of PTR then is 2345?
No, the value of PTR is 23423.108. The value of target of PTR is 2345. Let's use the proper terminology. This is something that is extremely important. The reason that you see I'm going about it this way is that if you say it right, it will fit in your brain. But if you say it incorrectly, you'll never learn it. That's the most important thing. So I am printing the value of var 2345 is printed. I am printing the value of target of PTR, that's again var 2345 is printed. But if I'm printing the value of PTR, that's the address. Therefore, the address is printed. Are we good? All right. And let me see if I. Oh, give me a second. Okay, I'm gonna do something in here. I'm gonna turn off the screen and make it blank, but if I do that, then people in recording is gonna see it. So I'm gonna stop the recording. Resume the recording. I'm gonna do something else. I'm gonna bring up this guy over here, down, and set up something in here before I want to show it to you. So bear with me for a second. This is something that I really need to do. Seriously. Okay. Okay, so you'll see what I've done. I'm going to do something in here to kind of make this thing fit. So this is going to be, I'm going to actually use the exact same notes that we have over here instead. So all right, so this is the main that we had over there, right? This is the main that we have with this. So from what I said, I can do something like this. So I can essentially say pointer, PTR. Actually, let's continue the thing first. Give me a second. Give me a second. Save this. Okay, let's come back over here. So let's continue. So now that I have this one, let's do the same thing for the double. Okay, so we have digested it down to this point. I'm going to do something with the double. So I'm going to come over here. I'm going to say, okay, now I want to hold the address of dvar in PTR. Therefore, 132 is going to go to PTR, right? And now what I want to do is to say target of PTR is that double value. Well, wait a minute. Having this over here, did I mention what type of a thing this is pointing to? No, I just said pointer, right? So how the devil compiler is supposed to know what is sitting at the target? In the other one, I was doing wishful thinking. This does not gotta work. It doesn't know. It has to overwrite 4 bytes. It has to overwrite 8 bytes. They're two different things. So to actually do this, it won't be able to actually do it. This is wrong. To actually tell to the compiler what type of a thing I'm dealing with, I have to correct this by saying integer pointer PTR. To tell to the compiler, hey, what you are pointing to is an integer. And having said all that, now I can actually have the address properly set, and when I set the target, everything is good. Now, if I want to have a double, instead of having an integer pointer, I'll create a double pointer dptr. The size of the two are the same, so PTR and dptr, they're both 4 bytes, because they're both addresses. It's like an envelope. If you are sending that envelope to an apartment, or you're sending that envelope to a house, or you're sending the envelope to a government building, the size of the address is always the same. It's the target that is different, right? So in here, when I say double pointer dptr, I'm actually just telling to the compiler, hey, this thing is supposed to point to a double, not to an integer. Because of that fact, now the compiler actually knows that 132 is actually a double, and when I set it to something, everything's going to be set proper. Which means now I can say print the double variable, the value is going to get printed. If I say print the target of dptr, again, target of that pointer is a double, the double is going to get printed. But if I say print the dptr, again, it's just going to be an address. Exactly like what I've done to the other one. Are we okay now to this point? Do we understand this? Any problem down to here? Yes. Target of literally means target of. What is the target of my finger right now? What is the target of my finger? What is the target? That literally, it means it is, what is it targeting? Literally English target. Are we okay with this? So the question was, what is the target of means? I wish you had the microphone. What is the target of means? Essentially, target of means, what is the target? Okay, literally. Okay, so let's try this. So now, in here, yeah, I should be able to say integer, pointer, PTR, that's a pointer. Then I'm going to write integer value, or let's put it var, that's going to be 1, 2, 3, right? Now I'm going to say PTR is set to target of var, right? So now my, why does it give me an error? It shouldn't give me an error. Give me a second. I want to see what mistake I made. I didn't plan to do this, that's why it's a little... No, this should be good. Oh, I'm a bad boy. It's not target of var, you idiotic fool. It's var equals to PTR. Target of PTR. I said something and I typed something else, right? That's essentially what it is. So I have an integer pointer PTR, then I have a variable called var, then I'm going to say target of PTR is equal to, PTR will be, sorry. PTR will be address of var, and now I can actually say cout var, that's going to be the variable that's going to get printed. Now I can say cout target of var, and that's when the targets of variable is going to get printed. I'm going to put it in parentheses. Target of PTR, sorry. Okay. And I can say cout. I'm going to put just PTR, and the PTR is going to get printed. So if I run this program, you will see that. I'm going to go F10 and run it step by step and show it to you. So before we do this, I'm going to show you this slide one more time because I confused the heck out of all of you. Before we walk through this, let me put this at left and put this one at right. So we have the execution and the result. Now let's go back to here. So again, one more time. Whatever pointer PTR, let me go to the previous one that is integer, so it's going to be the exact same thing. Okay, so when I say integer pointer, PTR is a pointer. When I say PTR is address of var, it extracts the address of the variable, puts it at a pointer. When I say target of PTR is something, the value is going to change, then I can print all the values. We good? Okay, I'm going to do the same thing over there. So go back in here. So in here, I have a pointer, I have a variable, I put the address of the variable in a pointer, then I print the variable, print the target, and do such and such. Now I can actually say target of PTR is set to 23456. Now I'm going to say cout var, and to double check and make sure everything is good. So let's continue. It's going to recompile it to fix it. So now PTR is all garbage. As you see, there is no address in here. As soon as I say, and var also is garbage, but now it sets to 123, 123. Now I'm going to set the PTR to address of var. Now it's not garbage, it's an actual value. Okay? Now I'm going to print the var, that is 123, print target of PTR. Again, it's going to be 123. Print the PTR, that's the address. Now I'm going to say target of PTR is 23456. Therefore, var will change to that value. And that's essentially what all the pointers are. Okay? Now, why they didn't teach you like this and they asked you to put all star and star, we're going to go through it. So you'll see exactly why. So when they created the C language, the people who actually designed the language didn't want to type a lot. That's why they presented pointer as asterisk. They said whenever you want to use pointer, put an asterisk instead. Therefore, all the pointers are changed to asterisk. You see that? So this is the syntax now. So that asterisk that you see is pointer. You shouldn't call it integer star. That's wrong. You should say integer pointer, because that asterisk, when it comes after the type, it's a pointer. Then, what they did, they represented address of with a single ampersand. So whenever you see an ampersand coming before a variable, that means address of, not ampersand. Never say that. So what you see over here is essentially dptr is equal to address of dvar, and so on and so forth. And to make the matters worse, they actually make the target of represented by asterisk 2. But the difference is that this asterisk comes before a variable. So if asterisk is before a variable, it means target of. If the asterisk is after a type, it means pointer. You have to remember that. If you say it, then it's going to be fine. So, going back here, as you see, all the targets of are changed. Now this is real C syntax. So essentially, target of and pointer are both presented by asterisk. If asterisk comes after a type, it means type pointer, whatever the type is. Employee pointer, car pointer, integer pointer, double pointer, whatever. If it's like this, integer pointer, double pointer. Now, because it was C, I had the struct, you don't need to have it in C++, so employee pointer. So if asterisk comes in front of a variable as a unary operator, then it means target of, which essentially means A is equal to target of P. Never say asterisk P. Target of T is equal to X. Or target of A is equal to B multiplied by target of C. Okay? Now, the thing that you need to remember, how to actually understand what asterisk is. When you look at the asterisk and life is beautiful, you look at the asterisk and say, I know that. That's multiplication. Okay? When you see the asterisk is coming after a type, that's pointer. When you see the asterisk is coming before one variable, that means that variable is a pointer and you have target of. So that's that. And this one is going to be E is equal to target of M multiplied by C multiplied by C. Okay? And that's that. So how the devil this thing actually worked? This is the magic behind it. I said define target of to asterisk. Wherever you see asterisk, replace it with target. Wherever you see target of, replace it with asterisk. Whenever you see address of, replace it with an ampersand. So that's all I did. I just search and replace with define. So compiler will actually go through it. Remember about preprocessor directive? It actually goes through it, replaces it, and that's why it works. And that's, I just wanted to prove it to you. That's really what it means. Don't give pointers extra credit. They're just variables. And you just set them to values and use it accordingly, and that's all. So that's all about pointers. That's the C pointer thingy. Now, with respect to arrays, pointers are almost the same thing. So when you're dealing with arrays, you have the memory, and when you create a single variable, obviously you have just one variable, and the pointer and everything, we know exactly what it is and all the good stuff. But when you actually create an array, there are series of variables happening back to back. And the name of the array is not actually a name. It is actually a pointer, a constant pointer that points to the beginning of all of them. That's how arrays are designed, using a pointer. Any name of the array that you see is actually a pointer of that type. So when I say integer AR5, AR is a pointer to an integer that points to the very first one. And the index in front of it, it tells how many of that type you should jump forward. When you put 0, it means from AR, go 0 further, which means first one. When you say 1, it says go 1 integer further. Because integer is 4 bytes, it's got to go 4 bytes further. When you say 2, that's why indexes in C start from 0, not 1. In many languages, actually start from 1. And that's what it is. That's why if you say target of AR is 2, 3, 4, 5, even if it's an array, it sets the first one. If you say AR2, it sets the third one. You can actually say target of AR plus 2. It means the same thing. You are saying add the address of 2 integers to AR and set the target to something. It sets it. You can literally treat an array like a pointer. That's why in a function, when you are receiving an array, you can either have an array notation or a function, a pointer notation. They're both exactly the same. And that's that. So that was an IPC 144 lecture. That I usually give it over here when it's needed. So I'm going to just put over here pointers. I'm going to call it fake pointers, C, A, B, C, D, E, fake pointers. Okay? And now I can actually put the pointers up. So I'm going to go to pointers and stop the execution. And bring that up. So back to what we had. It's actually 2:26. I have like 10 minutes, but it's okay. So make your computers ready. We're going to start soon, but let me just go to the notes that we have. Three, 4, 5, NRA. I'm bringing back the lectures up. Oh, we have it here. There we go. Okay, so this was the pointer that I talked about. That was the pointer note that I put over there, Control V. So this is real pointers. Okay. Now, what is null pointer? Null pointer essentially initialization. It's a literal value creates, so null PTR, when you put null PTR, it literally is a 0 being casted to void pointer. Okay, so it's a pure 0 address. You can put it in anything. So pointers are set to null. You always, as I mentioned, you can always use type def to make your pointers easier, which essentially means you can do stuff like this. Let me make this empty. We talked about it in type def, so you know exactly what they are. You can do stuff like this to shorten the type defs. We talked about this before. So instead of actually writing a ginormous thing, you can actually do it like this. So either do it this way or create a pointer just like that. A generic pointer essentially is a pointer that is pure pointer. It's not, it doesn't know what is the target. So remember the original pointer we created? The original pointer that we created is essentially what a generic pointer is. The one that we created, fake pointer that we created, set pointer, we have that in C. It's called void pointer. If you create void pointer, it means it's pure address. I don't know what is the target. The good thing about it is that because it doesn't have a type, you don't need to cast any pointer to put it in there. A void pointer can be set to an integer pointer, to a double pointer, to an employee pointer. Any address can go into a void pointer. And that's that. I'm doing static cast over there for it to actually put it back. So if you take a void pointer and you want to put it in a regular pointer, you have to cast it. But the other way, you don't need to. A void pointer can be set to anything. So as you see address without a type, you can put it in there, but you have to cast it back if you want to reuse it. Void pointers are very useful to do generic stuff. Now I'll explain to you what do I mean by that. For example, if I want to get a hexadecimal dump of a piece of memory, I want it to be any type of a thing that I want to print the hexadecimal dump out of it. If I take a look at the function over there, hex dump. Now, as you see at the beginning, I'm receiving a void pointer. Because it's a void pointer, it could be called with anything. Take a look at line 18 and 19. I can say hex dump address of I or hex dump address of X that is a double. I don't need to cast it to anything because the receiving argument is a void pointer. And a hex dump essentially means I want to look at the content of the variable in byte pieces, which means all I need to do is to receive its size from the function, cast the target to a character pointer, and then go piece by character. So with this void, I could have created over here a character pointer, but then if you wanted to call, you had to cast it every single time. I don't want to do that. I want to get the address of anything. So this hex dump of mine can receive the address of any type of thing that I have. And it actually shows the content of each variable that you have. Copy. It can print address of anything with the hexadecimal value. Builders, what did I do wrong? No. Does not match the function type. What do I have? Oh. So I have void and integer over here. Why is it return 0 in here? Sometimes I do things, sorry. I had to return 0 over there. So as you see, the bit pattern of 2345 integer is 98090000. That's how it actually sits in memory. And this is the bit pattern of the double value in memory. When I say bit pattern, you remember what it was. 9 essentially means 10001, hexadecimal stuff. Remember, you know that, right? Okay, so it's essentially the bit pattern. So that becomes a bit pattern. And it's as simple as that. So generic pointers work that way. So these are all stuff that we had from old times. Okay? GH, X dump. Now let's get into actually C++. So very first thing we need to remind you of are references. When we are dealing with references, essentially what we mean is that we can actually give things new names. So essentially if I have an integer value, I can create an integer reference and set it to X. Therefore, I don't have two integers here. I have one integer with two names. One is X, the other one is ref. Are we okay with this? Everybody's clear on this, right? Now, we call this an L value reference. Okay. L value and R value. Let's put it this way. Left value and right value. What can you put at left side of an assignment operator? A variable in which you can put something in, right? Right? Can you say 20 is set to A? You can't. 20 is not an L value. An L value is a variable in which you can put something. Okay? We call that an L value reference. So what you see over here is an L value reference. Now C++ represents you with a new type of reference, and that we call that one an R value reference. What is an R value reference? It's a reference that keeps the name, keeps the reference of things that are either they don't have a reference or there are things that are just about to die. Any temporary value, we call those things R value. So take a look at this. So this one is an L value reference. Now, when you put two ampersands after the type, you are actually telling, I want an R value reference, which means when you are receiving the value, that should be something that is either temporary or an R value. Now, take a look. If I say over there print X, the first function will be called. When I say print 20, it knows 20 is not an L value, it's an R value. Therefore, the R value reference will be called. So you can actually detect by overloading a function what you are receiving, if it is a temporary value or it's a real value. You can actually detect that. Okay? One more time. By doing something like this, you can actually detect what's coming in has a handle. Is it a value that exists out there, or it's just a value or a value that is about to die? Okay? So let's put it like this. Take a look at this line 12's execution. What do you see at right? You see an R value, right? What did I do at line 12? I created the copy constructor of X, of int. And I said, create a temporary int out of X. That is an object. It's not a literal value. But it's an object that is about to die. It doesn't have a handle. It's a temporary thing. That is an L value, an R value too. This is an extremely important thing in C++ that makes the language much faster. Now, I want you to listen to me carefully. And I hope that you can remember this from your OOP345 era. When you had a class that had resources in it, what did you have to do with that class? When you had a class that had dynamic memory allocation, what did you need to create in it? Rule of 3, which means it had to have a copy constructor, it has to have a copy assignment, and a destructor implemented or blocked. So you had to decide what you want to do, correct? I may not do the quiz today to finish this topic. You can do the quiz the next day you are coming in. It doesn't matter. You may do 2 quizzes that day. So, what is a copy constructor? If I have a cup of coffee, or I have a bottle over here, right? Or a cup of coffee. When I have a cup of coffee, in real life, okay, if I want to, I'm a function, I'm returning a cup of coffee to this lady, okay? In real life, what I have, I'll give my cup of coffee to the lady and I don't have anything, right? But in C++, that's not the case. This cup of coffee has resources. What is the resource? Coffee. So what do I do? What does she do? It's stupid when you think about it. For me to be able to give the coffee to her, she's gonna look at my cup and sees there's a coffee. It brews the exact same coffee that I have and takes it. So essentially, I am telling her what do I have. She gets a copy of my coffee, then I throw my coffee away. That's how C++ works. That's how copy construction works. Right? Now we say, that's not a good idea. I am handing you a coffee. I cannot give you that cup because it's mine. It's in my function. But the coffee inside is not mine. It's a dynamic thing. So what she can do is just bring her cup to me, and I can move my coffee to hers. And I bring it back. She gets the coffee. I just throw away the cup, not the coffee inside. Do you understand this? Does that make sense? That's what we do with this. When you create a copy construction with 2 ampersands, it becomes a move constructor, not a copy constructor. So what you can implement inside, because now you can detect what is coming is temporary, because when I'm returning an object to the lady, that object is temporary. My scope's got to be over, that object goes to garbage. She can detect that it's temporary using that, and therefore just implement a code to receive my data, and therefore not to create anything. It's amazing. So all that copying and allocating and resetting and all the stuff is gone. Instead of, so in a copy constructor, what did you do? You received my data, you received my class, you measure the size of my data, you allocate enough memory, you copy every individual data of mine over here, then you throw everything that I have away. I delete my data and it's gone, right? In a move constructor, you receive my object, you check, is it temporary? Yes, okay. So if it's temporary, all I need to do is to create one pointer of the type of your data and point to your data and tell you, just don't point to it anymore. So the one that is being moved sets the pointer to null, the other one sets the pointer to the data, and data is moved. And we're done. So that becomes what we call a move constructor or rule of 5. That is implemented using this. So, and the whole concept goes in here. And that's what I want you to know. So this is something extremely important. We're going to go to move constructors the next day you're coming in. So that's that. And I'm going to end the session today, right over here. So you have to, let me just write it down over here. And we have time for your quiz too, actually. I thought we don't have time, but we do. So I'm just going to write down over here where did we end? So we are on pointers and references. So today is September 11th. Okay, prepare your computers for the quiz. Again, feel free to write garbage. It doesn't matter. I want you to just write whatever comes to your mind for the quiz that I'm going to give you now. Yes? It has to be on that computer, otherwise it's not going to work. And you cannot have any start button of anything. So because, as you see, it doesn't work. So just click somewhere so it goes away. Okay. So open My Apps. My Apps. Open. Everybody open My Apps. Okay. Check the box first. Close it, please. When My App comes up, you check it and you say set. Set as, there we go. So that's that one. Then log in. So actually, I gave you the wrong one. Okay, now log into it. And I'm sorry, I gave you the wrong thing for that, but you're good. So log into My Apps, please. I'm going to